Uh, just give me a minute.
Mm.
Okay. What were you saying?
I was saying that me and my tutor are still working
Okay.
on, yeah, and I wanted to know when I let you know, can I
Which
redo the assignment?
which assignment now?
Module 5.
Okay, fine. You can redo it. Did you
Yeah,
already submit something?
yeah, I did.
Okay, so I will clear it. Okay, and you can redo it.
Okay.
Okay.
Yeah, because I didn't want you to open it yet because we're still working on it.
Okay. All right. Fine and good. Let me see what is in module 5. Okay, module 5 is analysis of variance. Okay.
Yeah.
And we are gonna talk about it today.
Okay, and yeah, for module there I checked on Blackboard and there's no module 6 posted. Is that because we don't do
The
assignment this week?
module 6 is gonna be posted today. As a matter of
Oh,
fact, I think I already posted it.
no, it's not there.
I find that very strange. Yeah, I posted the module 6, but I opened it. I forgot to open it after I posted it, but I opened it today.
Oh, you just did it?
I just opened it today, but it's gonna be moved anyway.
Okay.
It's gonna be moved. We're gonna catch up somewhere along the line. We skip what you know, and not be absolutely necessary. But we'll give another 5-7 minutes to see if other students are gonna come. Okay, so be patient. Okay, we are back in business. So let's take it from here. All right. The last time we met, we looked at a test of hypothesis for two populations, and our objective was to ask whether there's a significant difference in the average of two subpopulations or two populations. For example, if you wanted to test union workers versus non-union workers and see if there's a difference in their wages. If you wanted to test people from Brooklyn and people from Queens and ask, is there an average, is there a significant difference in the average family size of people that live in Brooklyn compared to people that live in Queens, or the average age of the population, or the average age of houses, the average size of houses. For example, you compare the average size of houses in Hollywood compared to average size of houses in residential houses in downtown Brooklyn. Okay, and you say to yourself, yes, there's a significant difference. Or you compare the average size of houses in Borough Park to the average size of houses in Bed-Stuy and say, there's a difference or there's no difference. Compare the average age and so forth and so on. So you can compare averages for any two populations. So now we are going to extend this comparison of averages to 3 or more populations. We're going to compare the 3 or more populations, and we're going to use a totally different statistical procedure. One thing that I need to talk to the class about, and I would really prefer when everybody's here, or at least I'm going to send a message, please pay close attention to the homework assignments because the midterm exam is coming, and all of it is not going to be multiple choice. I'm going to have written questions where you actually show that you can test a hypothesis, okay? And it's very, very important because this class is really based entirely on inferential statistics. So I'm going to share screen, okay? All right, are you seeing my screen?
Yeah.
All right. So we're going to continue our hypothesis test. We're going to test 3 or more populations, okay? 3 or more populations. And so this kind of test is called analysis of variance. We're going to take the simplest form of analysis of variance, which is a one-way analysis of variance or one-way ANOVA, okay? There's two-way analysis of variance, and there is also two-way analysis with interactions and what have you. So for this class, we're going to take the simplest form of analysis of variance. And so the objective is that you look at 3 or more populations. There could be 10 different subpopulations. There could be 4, there could be 5, there could be 7. And so your whole objective, your null hypothesis, is that the average for all the subgroups are the same. The average age of people in Brooklyn, in Queens, and in the Bronx and in Staten Island are the same. So you're now looking at 4 different subpopulations in New York: Brooklyn, Queens, the Bronx, and Staten Island. Okay, so you want to compare these 4 and say the average age of the population is the same, or the average age of houses, or the average size of houses. Okay, you have to find a way to measure average size. For example, the amount of living space. Okay, in houses in those 4 boroughs. And so your null hypothesis is that mu1 is equal to mu2 is equal to mu3 is equal to mu4, and as many subgroups as possible up to k. Okay, and so the average is the same. Okay, the average of what? The average age, average size, the average family size, and so forth and so on. Okay, so the alternate hypothesis is that at least one pair, we'll call that mu I is not equal to mu j, for at least one pair of the populations. Their means are not equal. Okay, and one pair could be that 1 and 3 are not equal. Okay, your null hypothesis is that everybody is equal. Your alternate is that at least there's one pair. Could be 1 and 3. Could be 1 and 4. It could be 3 and 4 are not equal. Could be 2 and 4 that are not equal. And so if 2 and 4 are not equal, then you reject the null hypothesis. All right? And so how do we go about doing that? How do we go about doing that? How do we go about testing the null hypothesis that every subgroup is equal to the other with regard to some characteristic, like the average age or the average size or the average something? Now, okay, of course, our objective, we're not going to do the equality of variances. It's also done using the same ANOVA. We're going to use ANOVA to test the hypothesis that 3 or more population means are equal. Okay, and then after that, suppose that you reject the null hypothesis that everyone is equal. Then you begin to ask yourself, which 2 or more are not the same? Okay, and we're going to use confidence intervals to test and interpret the differences. We don't have to use confidence intervals. We could use the regular Z statistic to do that. Okay, we might actually do it that way here. And this is what is called a post hoc test. Okay, let me write it down so that post hoc test. Okay, so once you reject the null hypothesis, then ask yourself which 2 groups are not equal in a post hoc test. We are going to use instead of using the Z statistic, and I'm not going to have you go and calculate an F statistic, but F statistic is easy to calculate if you have the numbers. But we're going to use what is called F statistic. The F statistic has two different degrees of freedom. Okay, there's something called degrees of freedom in statistical analysis. There's a numerator degree of freedom, that there is a denominator degree of freedom. Okay, the denominator degree of freedom is here on the extreme left column, 1, 2, 3, 4, and so 18 degrees of freedom. And the numerator degrees of freedom are up here. It could be 1, 2, 3, 4. It could be more. Okay, could be more. If you look at a typical F table, you see a whole lot more degrees of freedom in the numerator. All right. All right. So, how do we proceed? Okay. You take a sample from each populations. Okay. Take a sample from each population. The samples are randomly selected and are independent. Okay. And so you calculate the means. And our hypothesis, like we said, is mu1 is equal to mu2 is equal to mu3, mu4, and so on and so on. Let me just, okay, mu, okay, equal to mu4. Let's see if we can get something out of this. Okay, and let's just keep moving. Leave the fancy alone. Mu1, mu2, actually it should be mu3, and so forth and so on to mu4. I mean to mu k, whatever k is. K could be 10. Okay. And the alternate hypothesis is that the means are not all equal. Okay? If any one pair, 2 and 3 are not equal, if 1 and 3 are not equal, then you reject the hypothesis that everything is the same. And so you collect the data, and the data does not have to be the same sample size. These are different data. I mean, the calculation is somewhat tedious. It's not complex, but that is not our purpose in this class. We're going to simply learn how to use the F distribution to do the rejection or the not rejection of a hypothesis. Okay. All right. We calculate the means. Okay. We calculate the means of each group, and then we calculate the difference between the means of each group and an overall mean. Okay, that's a grand mean. But like I said, we're not going through that. Okay, we can do that in an advanced class after this, but not yet. Okay, and again, I'm just going through the same thing. You know, that the null hypothesis is that all the mu's are equal. Okay. All right. So, and I'm going to go through an example so that we can see what we're talking about. Okay. And so we select the numerator degrees of freedom and the denominator degrees of freedom. In this case, we have overall 18, and then there are 4 groups. As you can see here, there are 4 groups, 1, 2, 3, 4. Okay, and because there are 4 groups, then the numerator degrees of freedom will be 4 minus 1. That is why you have here, let's see, okay, that's why you have 3 degrees of freedom in the numerator, okay? And then 4 plus 5 is 9, 9 plus 7 is 16, 16 plus 6 is 22. So altogether, all the 4 groups give you a sample of 22. And so 22 minus 4 will give you 18 degrees of freedom in the denominator. Okay, so the F distribution we're going to look up is 18 degrees of freedom for the denominator and 3 degrees of freedom for the numerator. All right. And then also we select a level of confidence. Okay, so we're going to select a 0.01 level of confidence. And so if you take 18 degrees of freedom in the denominator and then 3 degrees of freedom in the numerator, then it will be 18 over 3, and which gives you 5.9. Does everybody see why we got that critical F is going to be 5.9? Hello?
I'm here,
Yes.
Professor.
Yeah.
All right. So when I say hallelujah, you say amen. All right?
Okay.
All right. So do you understand why we got 5.09 as the critical F statistic? 18 degrees of freedom in the denominator and 3 degrees of freedom, the intersection is 5.09. You see that?
Okay, yeah.
Okay. So let me ask you a question. What if the degrees of freedom denominator is 15 and the numerator is 2? What would be the critical F? 15 and 2.
What's it? 6.36?
6.36. Okay, so that tells me that you are following what we are doing. All right. It says you're following what we're doing. So the degrees of freedom will be the critical F will be 6.36 if we have 15 and 2. All right. If we have 17 and 3, or let us say we have 17 and 4, what will be the critical F value?
4.67.
4.67. So that means we're getting the point. All right. So when you then calculate, okay, which we're not going to go through that calculation here, but when we get the calculated F, then we compare F to the critical F. So this is the critical F, okay? And I'm going to call it F star. That is what my professor taught me in grad school. He called it F star, okay? Now, here the F star is 5.09. And so we reject the null hypothesis if F, the calculated F, is greater than the critical F. Okay, so here is the calculated F. I'm going to call it FC as the calculated F. All right. All right, so we have an example here. Okay, we're going to compare 3 styles of houses. Okay, think about a neighborhood. We're going to compare the average ages of houses, okay? And the null hypothesis will be that the average age of houses is the same regardless of style. There are 3 styles of houses. There's ranch, there is 2-story, and there is the tri-level, okay? And what could give rise to the average age of houses being the same? What could give rise to the average ages of houses being different across these 3 styles? Does anybody have an idea? So, Ms. Greenwich, do you have an idea why you come to a neighborhood and there is a difference in the average age of houses across 3 styles of residential houses? Yeah, tell me.
I don't know, Professor. I'm lost here.
Okay.
Yeah, I am a little
So
bit.
you come to a neighborhood. You come to a neighborhood, right?
Yeah.
And you have 3 styles of housing development.
Okay.
Is there any reason why the average ages of those houses will be different across those 3 styles? Think about it. So, Miss Morley.
It wouldn't be the neighborhood.
No, let's say in the same
No.
neighborhood. Let's say in the same neighborhood. There are 3 styles of residential houses.
Mm-hmm.
Can you give me one reason why the average ages of the houses could be different?
I don't know. I guess the way it's
Yeah,
built,
I mean, it's a lot of common sense now. The same neighborhood, you have 3 styles of houses, but the average ages are the same.
What year it was built?
What year was built? Why would the year that one style of house is built is different from the other style?
Mm.
Something easy for you to think. Think about it. Why would even the average sizes of the houses, why would they be different?
The sizes and the ages, we mean the square footage of the and the
Okay,
type?
let me help you to reason the kinds of things we do in statistics and the kind of reasoning we do. Now, there's a good reason why the average ages of houses could be different. Let us say you come to a neighborhood and there's housing development in that neighborhood. Do you get that point?
Yeah,
Right?
I got that point. Okay.
Good. And initially, they begin to build ranch. Right?
They began to build what?
They began to build ranch-style houses.
Okay, ranch style. Okay.
Yeah. So 2 years later, they
They
now
changed the
mix
style.
a ranch and 2-story.
Okay, got you.
4 years later, they begin to build ranch 2-story and tri-level.
Okay.
That's
is it the amount of money they have?
It could be any reason. It could be the choice that the people that were buying the house were making.
Okay.
It could be a choice that the developers are making to attract different kinds of customers.
Customers. Okay.
Right? It could be legislation. The initial authorization to develop the neighborhood, the city or the government says, no, you can only build ranch. And you know what happens in politics. What's going to happen in politics if they say you can only build ranch?
That you only can build a ranch house?
Yeah, let us say the government says initially you can only build ranch. What do you think would happen politically?
Everybody's gonna be building ranch houses in one neighborhood?
Yeah. Or the developers are told you can only build ranch. What is the next political thing that could happen? You all get involved in politics and we'll talk about, oh, well, the government is cheating people and all of that. What is going to happen next?
Everybody's going to protest. They want to change.
Yeah. People are going to put pressure.
Yeah.
People could start to put pressure. And who could put that pressure? Tell me. Give me an idea. Who could put the pressure?
Maybe the neighborhood. The people in the neighborhood.
People in the neighborhood. Who else?
People with different races.
Okay, who else? Those are people in the neighborhood too. Who else?
The developers also put pressure.
The developers could say, hey, we want to attract different kinds of customers. Everybody doesn't want to live in a ranch.
Yeah, because then they're not going to get whatever they want because
That's
they build one style.
That's correct. All right. Now, it could also be that initially you build the 3 kinds of houses, but more ranch than the other 2. And over time, then they begin to add more of the other kind. You get it?
Okay. I got it.
Okay. All right. So, but somebody comes in and says, I think the average size of houses is the same. I can think, or somebody comes and says the average age, because I do remember, or it appears I have read that initially it was all ranch, and then they began to add the two-story and the tri-level over time. So we theorize about it, and we go now and test. Let us see if my theory is true. So this is what you do, okay? I mean, you can use this to think about what happens, first of all, politically. This is number one. And so you have an issue to what do you call it? Test the hypothesis for political purposes, for policy-making purposes. But marketing, okay, if you're a student of marketing, this happens also. You are correct?
Correct.
So the developers feel that we want to attract more customers, different kinds of customers, and so they begin to put pressure. That's a marketing issue. Am I correct? So you can see how we apply statistics. We can apply it to public policy. We can apply it to marketing analysis. All right? We can even apply it to financial analysis. Okay? The developers feel that on the average, if you build a two-story house, then the cost per unit is going to be less. And you then attract more customers and you make more profit. That is financial analysis. Am I correct?
Yes, you are.
That's financial analysis. So you can apply statistics in different ways. All right? Okay. So in order to test a hypothesis about means, the average, you have to calculate the mean. Am I correct?
Yes.
That's how we do hypothesis testing. We calculate mean. What else do we calculate?
The critical value?
No. Before you get to critical value, you calculate the means. What's the next thing you calculate? We talked about it.
Standard deviation.
Standard deviation. Standard deviation. You get it?
Yeah.
Okay. So you can see, you calculate standard deviation. Standard deviation is summation x minus x bar squared and what have you. Now, so what we do then is we calculate f. Our calculated f is 7.49. So here we are testing the null hypothesis about average age of houses, right? All right. And so you have 105 degrees of freedom, okay, for the denominator and 2 degrees of freedom for the denominator. Why do we have 2 degrees of freedom in the denominator? Why? You remember how we calculated the degrees of freedom for the numerator? Let's go back. We had 4 treatments, am I correct?
Okay,
4 different groups. So the number of groups minus 1 gives you the numerator degrees of freedom.
Okay.
You get it?
Yeah.
Very good. Okay. And so, why do we have then 2 degrees of freedom here? How many groups will we compare?
That you have.
How many groups of houses?
With 3 groups of houses.
3. Do you remember them?
Oh, because 3 minus 1 is 2.
3 minus 1 is 2. We compared ranch, two-story, and tri-level. Is that correct?
Correct.
All right. And so we calculate our F. So what I want you to be able to do is to take this F, which is the calculated, and then compare it to the critical. Okay? Compare it to the critical. And the critical that we found based on our table Let me see if I can find the table. 2 and 105 was 4.79. Okay. There's 108 sample size. And so 108 minus 3 is 105. And so we use 2 and 105. And according to our table, is 4.79. I don't know if this table has enough. No, it doesn't have enough of F distribution, but F distribution is somewhere that the full F, the complete F distribution. And so for our problem, we have a critical value of 4.79, and the calculated value is what? 7.49. Do you remember that? Do you remember that the calculated value is 7.49 from this table?
Yeah.
Okay. And so we calculated to the calculated value is 7.49, and we compare it to the critical value of 4.79. Get it?
Mm-hmm.
And so since F, the calculated F is 7.49 and the critical F is 4.79. So what do? We reject the null hypothesis that range two-story and tri-level of average age. So we reject that null hypothesis. So we're now saying that at least there's one pair, either our range and two-story are not equal, or range and tri-level are not equal, or two-story and tri-level are not equal in average age. That's what we're saying once we reject that null hypothesis. We don't know which one. And what test do we say we're going to conduct since we see that we reject this null hypothesis and we say there's at least one pair of groups with different average ages of houses? What was the name of the test? Since we reject the null hypothesis, remember we said we're going to conduct a post hoc test. We now want to find out which two groups are not the same. Okay, the post hoc test helps us to find out which two groups are different. That's what we do. And so here we use the confidence interval. Okay, so I'm not going to take you through, you can use a t-statistic to do it, but we use a confidence interval to find out which two groups are not the same. You can see the color scheme here. So we compare tri-level to two-story. All right?
Yeah.
Okay, you see the confidence interval up here?
Okay, yeah.
Okay.
Yeah.
Now, if the upper bound and the lower bound are of the same sign, if they are both negative or if they are both positive, then that means that tri-level is different from two-story.
Okay.
Did you get that point?
Can you say that again?
Okay. You see, in order to find out which two groups, which pairs are different, right?
Okay. Mm-hmm.
Remember, you have rejected the null hypothesis that everybody is equal in age.
Yeah.
Good. So now you're asking yourself, which pair are different in average age? So we compare tri-level to two-story, we compare tri-level to range.
Okay.
It makes sense to you?
It makes sense, yeah.
Okay. So now, how do you then determine whether tri-level is different from two-story? You look at the confidence interval that is printed out, because I'm going to print it out and give it to you, right?
Mm-hmm.
Okay, ordinarily is something that you can calculate. You can use SPSS to calculate it, okay?
Okay.
If the confidence interval bounds if the signs are the same. Remember what I said, if the signs are the same, right?
Mm-hmm.
So when you look at the lower bound and the upper bound on comparing trial level to two-story, are the signs of the lower and upper bound of the confidence interval, are they the same sign?
They're the same.
So that means that trial level is different from two-story.
Okay.
Okay. When you compare trial level to ranch, are the signs of the upper and lower bound, are they the same?
No, they're not.
So that means you see that the trial level and the ranch are about the same age.
Okay.
There is no significant difference in their ages. You get it?
I got it.
All right. Okay. And essentially, you repeat the same thing here. You compare the two-story to the trial level. We have already done that. And you can see the signs are the same, which is already here. But you compare two-story to ranch, right?
Mm-hmm.
Okay. So are the signs the same?
Yeah.
Very good. So that means that two-story is different from ranch, right?
Yes.
So really, when you look at the three kinds of housing, you find out that it's the two-story that is different from the others. Two-story is different from ranch, and two-story is different from trial level. Right?
Yes.
Okay. But trial level and ranch are about the same.
The same.
Okay. So two-story differentiates the other two. You get the point?
Yeah.
Okay. All right. So, well, these are all the mathematical calculations that go into this. We're not doing this in this class. Well, if we had a higher level class, we would have then gone into all that mathematical calculation, and it's not tedious. Like I mean, it is tedious, but it's not difficult. It's not complex. Okay. Way back in the past, I used to go through all of this, but it's not necessary for the level at which you're going to be encountering this at this. If you want to really now become the statistician, then like me, then you have to learn how to do all of that by hand. But in those days, we used to do it by hand. These days, we do it using statistical software like SPSS. All right. So does anybody have any other questions for me today?
Yeah, Dr.
Okay.
Obi, I just wanted to know, can you go in on Blackboard and change the date for this this week's module?
Sure.
Yeah.
I'll do that. I will change the date.
Okay.
All right. And give you up to the end of the week, this weekend. And then next week, we're going to start talking about regression analysis.
Okay.
All right.
Mm-hmm.
This time next week, that will be the 11th.
Okay.
All right.
Yes.
Okay. Any other questions?
No, I finally understood the hypothesis, so I guess I'm on the right track now.
All right. I really appreciate your time.
Yeah. Have a good evening.
And
Yeah,
you
have a good
too.
evening.
All right,
Thank
bye.
you.
Bye.
Bye.